Now let's talk about how we represent our instructions in machine language. So we're going to convert our assembly language instructions into machine language. This is the binary representation of instructions. So we'll represent our instructions using ones and zeros because that's what the computer understands, what our logic understands. We're going to use 32-bit instructions to, again, use that principle of simplicity favors regularity. We have 32-bit data, so our instructions will also be 32 bits. RISC-V has 4 types of instruction formats: the R-type instruction format, I-type, and then SB-type and UJ-type of instructions. So if, technically speaking, each of these is 2 types of instructions, but they're very similar. And we'll talk about those SB-type and UJ-type. We'll start with R-type. So R stands for register. So R-type is a register type instruction where the operands are all registers. So we have a source register or 2 source registers, RS1 and RS2, and a destination register. And we also have some what we call control fields, the op field or opcode or operation code. And then we have 2 other fields that control what the operation is that we should perform or that the computer should perform. Funct7 and funct3. The 7 and 3 indicate the number of bits we use to encode those fields. So the function bits, 7 and 3 bits, with the opcode tell the computer what operation to perform. So here's our R-type instruction. We have the funct7 field, which is 7 bits, funct3, and then here is our opcode, which is a 7-bit opcode. And then we also have our operands. We encode our operands. We use 5 bits because we have 32 registers. So we need 5 bits, log base 2 of 32, to indicate which register to access, our destination, and our 2 source registers, RS1 and RS2. So here are some examples. Add is an R-type instruction, so we encode it using the R-type format. Here we have our add instruction. And we first encode the registers, so we use our special names, S2, S3, S4. We look up on our register table what register numbers those correspond to, and they correspond to X18, 19, and 20. So the destination is X18, RD, and the 2 source operands, RS1 and RS2, are 19 and 20. So in our RD field, we put 18. And now we go to our RS1, our first source register, 19, and our second source register, RS2, is 20. And so we encode our operands in the instruction. And now we also encode, what operation to perform. So we have an R-type instruction, and the opcode here is 51 with function 3 or funct3 and funct7 bits of 0. And that's how we encode an add operation. We wanted to add the 2 source operands, RS1 and RS2, and put the result in the destination. Subtract is similar, so we still have our, we convert our names of our registers to the numbers. So T0, T1, T2 are X5, X6, and 7. So 5 is our destination, and then we have our 2 source operands, 6 and 7. And now, so we still have 51 as our opcode, but funct 7 is 32 to indicate subtraction instead of addition. And so then after we write all those fields in, we write the binary value, so 0, 7 bits representation of 0, the 5-bit representation of 20, 19, 3-bit representation of 0, 5-bit representation of 18, and the 7-bit representation of 51. Remember, our opcode is 7 bits. And then we can also write this in hexadecimal by gathering groups of 4. It's 32, so we can start at either end, but here's our 3. And our hexadecimal digits are going to cross these boundaries of the fields. So we need to write this in binary first to be able to convert it to hexadecimal. So we have 3, 3, 9, 8, 9, 4, 1, 0. So right, we have 0, 1, 4, 9, 8, 9, 3, 3. And so here's our hexadecimal representation of that instruction. And the same thing for our add instruction, right? Once we've entered the fields, we write those fields in binary, and then we gather groups of 4 and write the hexadecimal digit associated with that group of 4.